covered in detail simple linear regression and have learned how to calculate the parameters a and b, which model the y-intercept and the slope of our linear model. And we also learned how to calculate the coefficient of determination, which we call r squared. And this value then tells us how much of the variability can be explained by our model. Now what we want to do is look very briefly at multiple linear regression and nonlinear regression. The learning objectives then are to understand how multiple regression and nonlinear regression can improve a model for an output variable with multiple inputs, and to understand when multiple linear regression and nonlinear regression should be considered. So just a quick recap. Regression analysis then is this formal mathematical approach to studying the relationship between a cause variable x and a resultant or effects variable y. And the way we did this, we used the least squares method. We took data, sample data, and we were able then, using this data, to calculate the coefficients a and b so that we could model the y variable a plus bx. And the way this worked was we would end up minimizing the sum of the squared deviations from the actual values of y that are measured from the values of y that are predicted by this line. We also had the coefficient of determination, r squared, as we just said, representing the proportion of total variability in the observations of y that is explained by the regression line. And we had an example. Here we have our x value, and here are y values, and we actually had data points for each of these. So we knew exactly for every x what y occurred. We wanted to model this. So we did our least squares method, and we came up with a line that would model these residuals, the sum of the square distances between each of the points and the actual line. And we had equations to calculate a and b. Now we also looked then at how we could calculate the r squared value to understand that only 31.8% of the variability could be explained by this linear relationship between x and y. So maybe not the best solution. What else can we do? And this then leads us to the idea of multiple linear regression and nonlinear regression. So when we have a reason to believe that a dependent variable y is influenced by several independent variables, for example, x1, x2, x3, then we would use multiple linear regression. So, and this would be, the model would have this form: y is equal to, so again, a, so alpha, plus beta 1 times the first influencing variable, x1, then a coefficient beta 2 times x2, beta 3 times x3, and an error value. Now, this then is our true model, and what we would do is the same procedure as simple linear regression. We can then use actual data to come up with the values of a and b as we did before. So the formulas can be developed the same way. We would minimize the sum of the squared deviations for every value. The coefficient of determination can also be calculated, but the mathematics for these formulas is very complicated. So normally you would do this with a computer program, and that would make the work easier. And we're going to assume that you could do that here, but we want to show you an example to show how the multiple linear regression is used then to find this relationship this relationship for y in response to several different x variables. So we're back to our oven drying study. Again, we had this idea, we're looking at different variables to see how these affect the dry ability of our oven. So here's our y variable. In this case, x1 is relative humidity, x2 is hot air temperature, and x3 is conveyor speed. Now, probably without even doing a big experiment, you already have an idea which of these would affect the dry ability and how. So the goal, though, is to determine if there is a linear relationship between the dryability. So between, let's see, the dryability is equal to a function of x1, x2, and x3 for these three. Now, once we know this type of relationship, this more complex relationship than just a single or individual linear relationships, this would help then to adjust the parameters of the oven to obtain the optimal drying performance. So just for fun, I plotted the two of our three input variables, x1, the relative humidity, and x2, the hot air temperature, as a function, or excuse me, I plotted the oven dryability as a function of relative humidity, and then again, oven dryability is a function of x2. Now, this is the same here, this graph is the same graph we've seen before, where we had our linear regression and we saw that the R squared was about 31%, 32%. Here for the x2, it's very hard to see what's happening here. This relationship is very, very unclear. So what we want to do now with multiple linear regression is then to combine these two factors together, and of course with our conveyor belt, our x3, in that linear model to then see if we can get a better result, a better model. And what we see here is the result from Minitab of the regression performed on these three variables. And again, this is from our textbook. The computer output shows the estimates of these coefficients A, B1, B2, and B3. So here we have for the humidity, which is x1, the air temperature, which is x2, and the conveyor belt speed is x3. And we have our coefficient A, B1, B2, and B3. And so don't forget the Y is equal to A, in this case, plus B1, X1, plus B2, X2, plus B3, X3. And I wrote pluses because actually B3 is a negative 0.260, B2 is plus 0.000874, and B1 is minus 0.0019. So we see also we have here the R squared value. We're not talking about the other R squared values that said this relationship does a much better job. It actually explains 65.5% of our values. So now we haven't talked about standard error. We haven't talked about significance and p-values yet, but maybe we could just introduce this concept right now. The computer, you can put whatever you want in there, it'll come up with some kind of values. But what's important is that we need to test the significance of the results. Which factors here significantly impact the outputs? And in this case, they actually all do. They all have a significant impact on the dryability of the oven. And again, what we see is, for example, the humidity. So this is this part here. The humidity and the conveyor speed both have a negative relationship to the dryability, which you probably already figured out. If the higher the humidity or the higher conveyor speed, the worse the dryability. Hot air, though, is a positive relationship. The higher the hot air, the better the dryability. So this, of course, makes sense. And if we look at a picture of this, what we have here, here's the equation, y, the dryability is equal to this long equation. And here we had 20 different data points. And so this is the data points here in blue, the data pairs, xy pairs. And the model is in red. The multiple linear regression model. That's why I drew it without the dots. And you can see, I mean, you've got some discrepancy in some places, but it's not a bad model. This means that then you would be able to change your parameters to optimize the dryability of the oven. Now let's look then at nonlinear regression. When would we use nonlinear regression? And when you have some kind of curvature or nonlinear relationship suspected between variables, you can use a curvilinear model. And for example, this is just one example. You can have an example y is equal to alpha plus beta 1x plus beta 2x squared. And we did that earlier. We had y equals x squared. This parabolic relationship we were sketching before in the correlation lecture. So if you suspect that there's some kind of nonlinear relationship, you can also then use the computer program to find estimates for these values. And of course, it helps to have a good feeling for that. Additionally, if there's, for example, two independent variables where models can have an interaction term that's of the form that looks like this, where y is equal to alpha plus beta 1 x1 plus beta 2 x2, and then an interaction effect. Beta 3 is the coefficient then of this interaction between x1 and x2. So if we look at an example of nonlinear regression here, we have again the oven study, again the same x1, x2, and x3, and their effect on y. Now, what could be a nonlinear model that might fit this? And what we've decided to do, again, you have to have some thought here. Computer can really try lots of different things out for you, but in this case, we want to have a model of the form like this. Y is alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, the same thing we had before, but we suspect that this relative humidity and the hot air temperature have some kind of relationship. We think that there's a joint effect of the changed air temperature and the humidity is much more profound on the dryability than the sum of their individual effects. So again, in other words, if they are both high, then this would have even a more impact on the even higher impact on the dryability than if you just raised one and then raised the other individually. So let's look at how this works. Again, Minitab's doing this, and here you see your dryability y is equal to 1.98. That's your A minus beta 1 times x1, plus beta 2 times x2, plus beta 3 times x3, plus, in this case we have a beta 4, and we're doing it looking at x1 times x2. So humidity and hot air temperature. And so again, you've got your coefficients here. Beta 1 is minus 0.0314. Beta 2 is minus 0.00294. Notice that's a little minus now. And beta 3 is minus 0.0221. But the product of relative humidity and hot air temperature has a positive coefficient beta 4. And now our R-squared value is 89.2%, much higher than before. And again, we're not going to talk so much about the significance here, but let's look at the improvement of the fit to our model. And here again, so I plotted this out. This time we're in the nonlinear regression model. This again is our data points, the things we actually measured. And now our model here in yellow, the nonlinear model, which again I've written up here, follows our data points much more closely. So you can see how easily complicated this can be. Now in a normal type of processing, I know one of my master's students just finished a project with BMW looking at parameters going into welding for electric cars, and there they had, like, I think it was 30 key parameters. So, there it can get much more complicated. There you're going to be using different techniques, different types of data mining models. But for many things, when you have a process, you can find a few key variables, and linear regression may not be enough. So it is very useful to be able to use multiple linear regression or nonlinear regression to model the impact. And regression overall is a very powerful tool for understanding these relationships among variables in the process. And then this can be used then to great advantage in improving process and product quality.